Hello, class. We're going to continue the lectures in Chapter 8. This is Section 8.3, and this deals with confidence intervals using proportions as our point estimator or our mean. And again, because of the central limit theorem, all this calculations actually are valid. And so they're just super similar to what we've just did, except a little bit different calculation for the mean or the point estimator and the standard deviation for the central limit there. So let's just get right at it here. So the idea here is confidence levels for proportions now. And the idea here is that we're going to use this as an example. So we have 800 parents and 632 of them say music education has a positive effect. So the idea is now using this idea of a central limit theorem for the proportion. And the proportion is the total positive, which would be 632, divided by 800, which is our n value. And we're going to use that as the mean. And the calculation of the central limit standard deviation to calculate the margin of error, just like we did in the last section. And so here are a few definitions. And again, the population proportion we're defining as P, and that would be the probability. And then the idea of X being the number of individuals in the positive, which this would be 632. Our sample size here of N would be 800. And so the sample portion is X divided by N. And so in our calculation, we would take the 632 and divide it by 800 and get our 0.79. So you could say 79%, right, of the parents believe that the music has a positive effect on their kids. And so the question is, let's generate a 95% confidence interval. So what is the high end of that positivity rate, if you think about it, and what's the low end of the positivity rate? And so the idea again is we need to find that margin of error. And where that comes in is here's our point estimator, which we think about as our mean. And this is the central limit theorem standard deviation for proportions. If you remember, if you could go back in section 7.4, I believe, it would be P times 1 minus P divided by N. And here's our margin of error again, right? So whatever z-score correlates to the confidence interval, you use that, and then you multiply that by the standard deviation from the central limit theorem. Poof, out comes this margin of error. To get the high end, you add it, and get the low end, you subtract it. And so let's walk through this one example here. Whoops, clicked on the wrong thing. So as we stated in the original problem, we had X equals 632, and we had N equals 800. And so with regards to this p-value, that would be 632 divided by 800. That would give us a value of, there we go. I don't know why my mouse wouldn't move, 0.079. So that's where we're at so far. Before we continue, I've missed one slide, but I could easily go back to it. There's a criteria that has to be met, just like any of these criterias. And the criteria is followed, so we could use this theorem, right? And first of all, they have to be random. They use the word simple random, but they just have to be random. And the population is at least 20 times as large as the sample. And so in this one, we don't know how many total parents there are, but if you think about it, between the ages of 5 and 18, you would think that there's way more than 862, I think it was. And then the items in the population are divided into two categories. And this is kind of appropriate right now because you could think about the two categories of election, right? You vote for one person or another person. And so this is voted for parents that think that music is positive, and then obviously the other ones would say negative. And then the sample must contain at least 10 in each category. So in this case, we comply with all of them, right? Because if you subtract 800 minus 632, you could see that that's 168, and that's also greater than 10. 632 is greater than 10. And if you think about it, there's way more parents than 800 for kids age 5 to, I think it was 16, with regards to that. So now we would walk through the calculations. So what do we need to do? Well, first thing we need to do now is I'll go back to the whiteboard and kind of walk you through this. So the first thing we need to do is to find what I like to call the standard deviation of the central limit theorem, right? And that for the binomial style proportions looks like this. So when you do that calculation, let me get all the right numbers here. It would be square root of 0.79 times 0.79, all divided by n. Calculator comes in handy here, and you'd get 0.028225. So then we said we want a 95% confidence level. Well, again, what'll come in handy is that little chart of the key z-scores of the different confidence levels. And you could see that when we go to the 95% confidence level, the z-score here is 1.96, and you see that right in the table here. And so going back to the whiteboard, with the z-score of 1.96 or 95% confidence level, we calculate that idea of the margin of error. And so that would be 1.96 times this crazy number. And when you do that calculation, okay, I put it on pause for a second because I wrote down the wrong number. So this was actually the answer, and I skipped a step when I was writing down. So let's go back to this and put in the right number here, which should be 800. And then when you do that calculation, you see when I looked at my notes and I wrote the wrong number down. And so it should be 0.0144. And so now it's this number times this z-score. And so when you do that, 0.0144, see what I did wrong is this is the actual answer of multiplying those two together. Sorry about that, but just a copy error, looking at my notes. So this is our margin of error. So this is the central limit standard deviation for the proportions. And when you multiply it by the z-score, that gives us our 95% confidence. That's where we get our 0.028. So what is our high end number? It would be 0.79 plus 0.028225. And if we round to 3 decimals, it would be 818. And then if we go 0.79 minus 0.028225, again, rounding to 3 decimals, you would get 0.762. So again, I always like to, I need a little space here, so I'm going to erase this. I always like to draw the little bell curve to make sure everybody remembers what we're actually doing, right? So all this is predicated on the fact that the central limit theorem allows us to approximate all these calculations using the normal distribution. And so if our mean here is 0.79, that is a bad, let me try one more time. One more time to get a little bit better bell curve. Not really. So that would be 0.79. And then at the high end here, that would be 0.818. So almost 82% at the high end would think it's positive. And at the low end, it would be 0.762. And so remember, this would be 95%. The idea that if it was approximate a normal distribution, the area between there would be 95%, right? And so the idea of what's left is 5%, right? 100 minus 95 is 5%. So what we have over here is 5 divided by 2. So that would be 2.5% on this side and 2.5% on this side. And remember, all of this adds up to 100 again. Okay, so that ends the first of, I think I'm going to do 2 recorded lectures for this section. This is section 8.3, and it's using confidence intervals via proportions because of the central limit there.